Hello, everyone, and thank you very much for joining this Photonics webinar entitled Advanced Materials for Energy Photonics. We hope that you will find the information shared today useful. So regarding MDPI, we are a pioneer in scholarly open access publishing with the headquarters in Basel in Switzerland. And we have been pleased to serve the academic community since 1996. And our mission is to foster open scientific exchange in all forms through open access peer-reviewed journals. And our portfolio includes 469 diverse and open access journals, including 460 peer-reviewed journals and 9 conference journals. And Photonics is an international scientific peer-reviewed open access journal on the science of technology and technology of optics and photonics, published monthly online by NDPI. So for today, we'll have a short introduction by our chair, Dr. Kyo, and afterwards we'll have presentations by Dr. Patana Sadayo Wong and Dr. Garute Dat together with Dr. Zhang. And afterwards we'll have a Q&A session, and at the end we'll have a closing of our webinar, also shared by our chair. If you have any questions, of course, please share them in the Q&A session or Q&A box, and we will afterwards respond to each of them. So, as mentioned, our chair is Dr. Kyo from Southern University of Science and Technology of China. And he is an associate professor in the Department of Electrical and Electronic Engineering with bachelor engineering and PhD degrees from NTU Singapore. So I would like to now give the floor to Dr. Kyo, and we hope that you will enjoy today's session.
Okay, thank you, Arina, for this introduction and also the facilitating our webinar. So I'm the Angu Gujo from this Southern University of Science and Technology. And it's my pleasure to be chair of the today webinars on this advanced materials for energy photonics organized by the Photonics channels. So we are honored to have the 3 speakers, Professor Pachaya from the VITEC, Thailand, and the Professor Sakafat from this Tsinghua Shenzhen International Graduate School, China, and the Professor Chen Yong from this Hong Kong University of Science and Technology, Guangzhou campus. And then to share their latest finding in the perovskite and organic-based optoelectronic devices. So let me introduce our first speakers. It's a Professor Pichaya. He is from this, currently is assistant professor at the VITEC. He graduated from this Imperial College of London, and then also under the supervision of the Professor Thomas Anapoulos. He's a very famous in this organic, the semiconductors, and it's after that he at the same time he joined as the VITEC as the lecturer, and then after that promoted to this assistant professor. And also he received several prestigious awards such as the Margin Investigator from the Journal of Material Chemistry C, and also the Thailand's Young Scientist Award, as well as from the research grants from this is a National Research Council of Thailand, and as well as the U.S. Air Force. And also this is in addition to the academy, he also have this working as a CEO and CTO of this spin-off company called this Cleantech and Beyond. So today his talk will be the coordination electronics, unlocking the potential of hybrid organic inorganic system for semiconductors and devices. So without further delay, I will hand over the floor to Professor Pachaya.
Thank you very much, Professor Kyo and MDPI for the invitation to join the webinar today. And I'm glad to meet with all the panelists as well, Professor Yong Zhang and also Professor Sak Safakas.
Yes. Yes.
Apologies about that. Let me start sharing the slide. Right. So the topic is about maybe a little bit unusual materials that have not been very well known yet in electronics, but that's something that I hope to change, basically to introduce more of this intrinsically hybrid organic and electronic materials to be used in electronic and optoelectronic devices. Okay. And I will basically talk about some background and like material designs, and as well as a key challenge, which is the main limitation that why like this group of material has not been widely explored yet in devices, and that is the processability issue. And before that, just a quick introduction about Vistech. We are a young university, so this year we are celebrating our 10th anniversary. We were founded in 2015. We are postgraduate level only university, so PhD and master's levels. We don't have undergrads here. Private university, we were founded by these first 5 companies. So a group of oil and gas, petrochemical complexes. So these big industries in Thailand. And later we were joined by energy companies as well as like the major banks in Thailand, Kasikorn Bank, SCB. So despite our young age, we are too small. So the total the total members of universities is about 350 students with about 30 faculty members. So usually we cannot get into like the usual rankings. Some of the rankings that we can get into is the one that measures like the quality of research. So we've been doing quite well on the like Nature Index ranking run by the Nature Publishing Group. Okay. But they don't look only just Nature papers, but basically the top journals within each field: chemistry, physical sciences, life sciences, and so on. We are in the eastern part of Thailand, about 2 hours from southeast of Bangkok, so in this region. And we are here in this district. So actually, if you search the name of our district, you will see this picture of durians, because this area is actually agricultural. So the campus is surrounded by plantations, basically. So the jungles and plantations, like you see the hills in the background. There are actually a few like wild elephants living up there. So once in a while we get notifications on our phones that, oh, elephants in the area, like not on the campus, but like the area adjacent to the campus. Try to avoid that area and so on. Currently we have 4 schools. So 1, 2, 3, 4. Focusing on materials. So this is the school I'm from, School of Molecular Science and Engineering. And then we have School of Energy Science and Engineering, Biomolecular Science and Engineering, and then Information Science and Technology. So these are the 4 key areas that we do train PhD students as well as conduct frontier research. And in the subgroup within the School of MSc, we have 3 people working on semiconductors. Professor Vinit Promarak, an organic chemist. So he synthesizes a lot of like novel organic compounds from small molecules to polymers. Myself, that I will discuss a bit more later. And then our new faculty member, Dr. Vacharapon, also working on perovskites as well as hybrid materials as well, metal and organic coordination polymers. Okay. And in my group, so we work from material design, fundamental, and then now the focus is on the processing, basically. So among the materials we work with, one of the main focus is on coordination polymers, which I'll be talking about today. And then we process them into thin films, characterize them, and then make them into devices. And one of our devices, thermoresponsive materials that we made into smart sensors. Then we also spun off into a company called Cleantech and beyond. Okay, so about the main topic today, so coordination polymers. Coordination polymers, they actually show a very wide variety of structural versatility. Early on during the early explorations, so the main interest is we can use ligands to help position metal atoms into specific configurations. For example, molecular wires, like in this case. So we have this cadmium lined up into a one-dimensional structure, and they are fixed in place by this ligand. Similarly, we have here the platinum here, although interconnected by the iodine, but can also be arranged into like one-dimensional molecular wire. And this is another example, and also with a famous ligand in the middle, tetrathiafluvaline. And on the other hand, we can also use the metal nodes to construct like pillars to lock the organic moieties into places. Like in this case, this example show. So we have this like sort of spiral of this metal nodes here, and then we have the organic semiconductors in the middle. And with this pi-pi stacking, then it increases the charge mobility. So the researchers also show that by carefully adjusting the size of the metal ions, then we can pack the organic moieties closer to each other, and that increases the conductivity significantly. Recently, we are also having a project where we try to link up like well-known organic building blocks. For example, thionyl-thiophenes, units that are widely used as a building blocks in organic semiconductors, but usually they are linked by CC bonds, which also allows for like rotational degree of freedom. But in this case, you want to link them up by metal centers, like the one that we already have published is nickel. So we link them with nickel and then thionyl-thiophene structures like this, and then they forms into flat one-dimensional ribbons, basically, and then they show very nice packing in the particle form. Okay, but then one of the key challenge for all of this coordination polymers, despite their structural versatility, is that they are very difficult to be processed into thin film structures. So for device engineers, for us, our community who want to use semiconductors in devices, okay, solution processing is like one of the easiest methods to make thin films, right? But then these coordination polymers do not allow that. Usually they are highly insoluble in the common solvents. They cannot be processed using the usual methods that we can put down the films, and that then limits their applications in electronics and optoelectronics. Okay. And now I'm going to talk about the inspiration, how we can process like this CP semiconductors. So I like to take you back a little bit to like my starting point, basically copper thiocyanate, since my PhD time with Professor Thomas Antopoulos at Imperial College. So copper thiocyanate has a very unique feature. It's got a favorable valence band structure and also a good energy levels that allows very good hole transport. And the conduction band is very high in terms of energy, so it effectively blocks the electron. So it's been used a lot in organic solar cells, perovskite solar cells, as well as light emitting layers, and also in like photodetectors and so on. It's transparent, inorganic, and solution processable. So this combination is quite rare. So back in those days when I first started, basically N-type oxides were well-known transparent electron transporting semiconductors, but then the P-type ones were very rare. Okay. Then researchers started to look into like different oxides or doping the N-type to make P-type. That was not very successful. And then we looked at this like as an alternative material that was first used from the dye sensitized solar cells community by Professor Brian O'Regan. So I met him when he was at Imperial College as well. So we learned about this material from Brian O'Regan, that he successfully used it as a solid hole transporter in dye solar cells. And then we try to apply that as a semiconductor on its own as part of my PhD. So we successfully show that CuSCN copper thiocyanate is a P-type semiconductor on its own, can be used. It shows a very good field effect, can be used in thin film transistors, and also like basic circuit components. And also with the postdoc in the groups back then, we also demonstrated the use of CUSCN as a P dot replacements in OLEDs and also in OPDs. Okay. And as I mentioned at the beginning, the very favorable energetics and give them a very good performance. But CUSCN also requires a unique way of processing. Okay. So typically we use this diethyl sulfide as a solvent. So it's got sulfur and then two ethyl groups on two ends. Quite smelly because it's sulfur based, and very fittingly I'm in the district that makes durians, but it's also found like as a phytochemicals in durians as well as onions and garlic. So we found that actually the diethyl sulfide can coordinate very strongly with copper thiocyanate, and it produces a very beautiful crystals like this. And then so at the beginning, like, we were excited, oh, we discovered a new structure, but actually maybe just a couple of years earlier than this research group in the States, Robert Pike, reported the crystal structure of this material already. So it's a one-dimensional lacquer type with copper and thiocyanate, and then we have the diethyl sulfide cap on the bottom. So it shows a very strong interaction with copper centers in the CUSCN structure. Nevertheless, then they can still be removed by heating, and that's the usual way that we process them into thin films. Okay? And this is like the implication of this is that because this strong interactions, and then during the removal, actually it leaves a lot of defects inside. Okay, and then we show that indeed we have a thiocyanate vacancies around copper as studied by X-ray absorption spectroscopy, and we can heal the defects, for example, by using iodide, adding acid solid iodine, and then they separate into iodide ions, and then the iodide can heal the defects, recover the coordination environment around copper. So CUSCN as a three-dimensional structure processed with the diethyl sulfide, and then it can actually result in an intermediate structure. It can be many structures that I'll talk about later. And then we can remove this and then obtain back the original three-dimensional structures. So in this intermediate structures, actually, we can see that there are two ligands together. So the primary ligand here is a copper, the SCN, the thiocyanate ligand. And then the secondary ligand, which is weakly, like, or more weakly interacting with the copper, is diethyl sulfide. And this is sort of the core concept that we are developing right now. So basically, to process metal and the primary ligands as a original coordination polymers, then we add the second ligand that would weakly coordinating with the metal centers, but later that can be removed and more easily removed compared to the primary ligands. Okay. And we can also see this from like all of these ligands can be co-ligands with the CUSCN copper thiocyanate, and then they result in like many beautiful structures like 0D, 1D, 2D. Okay, and we can also tune the electronic properties of all these different dimensionalities, and we see that actually the 2D and 1D in some directions, or like in the 2D, so along the plane where we have the copper and sulfur network, we can still have some of the whole transport remaining. Okay. And in the 1D, it's become quite flat, but there's still maybe some possibility. But like the 2D, for example, is very interesting in this case. But there are also the additional states that are optically active from the ligands, especially if we have the aromatic ligands. And apart from the property tuning, if you notice that most of these ligands are actually liquid state at room temperature. So many of them can be also used as a solvent that based on the concept that I mentioned. And we also show one work here where we use pyridine-based ligands, okay, with 4 different substituents, and we can obtain 2 types of 2D structures, like more flat type, so similar to the blue phosphorine, and the other one is the buccal type, ripple type, similar to the puckered black phosphorine. So we can control the 2-dimensional morphologies of CUSCN. And as I mentioned, the optical properties, electronic properties can be systematically tuned This is by varying the electron withdrawing strength on the 3 position of the pyridine, for example. And then from this, doing okay with the time, right? So so this is a summary. So now we like to basically introduce a new concept for processing, so solution-based processing of previously very difficult to process materials, like the group of coordination polymers, metal thiocyanates, metal organococcogenides, and by using the secondary volatile ligands. So use them in excess, basically, in liquid state to dissolve the main coordination polymers, and then use that to process into thin films. And then with the right processing, then we can just selectively just remove only the secondary ligands, and then we have only the metal and the primary ligands left in the film, and then use them for device fabrications and so on. And yeah, we are trying to also generalize this concept to other types of coordination polymers, including also metal organic frameworks. And I'd like to thank the research group, as well as various funding agencies and also collaboration partners from around the world. So thank you very much for your the attention today. Thanks. Is everyone still
sorry,
there?
just now, I'm sorry that just now I turned off the speaker. Yeah, okay,
okay.
so, yeah. Okay, so thank you very much for the exciting talk. And so now I open the questions from the floor. Is there any questions or comments for this Professor Pichayas?
I have a quick question to Professor Pichaya. Can you hear me?
Yep.
Yeah. So you are using this copper thiocyanate as one of the whole transporting layer that outperform basically the traditional PEDOT-PSS. How about the stability concern? Is it better stability than PEDOT-PSS or conventional whole transporting layer?
The material itself is quite stable, but I think in several literature now have shown that there could be something's happening at the interfaces between, for example, gold and copper thiocyanate, and also the CuSCN and the active layer. So maybe some interfacial layers might be that's another sort of direction of research to fine tuning or understanding more about the reactions that is happening at the interfaces between CuSCN and the other layers. But yeah, the material itself is very stable.
I see.
Yeah. Like I recently saw papers that some alloying could occur if we have metal layer and the CuSCN. So like the metal from the electrode can actually diffuse into CuSCN and then cause some alloying. And there was one paper show that with, don't remember the interlayer that they put that stopped that metal migration, that improved significantly the stability of the devices.
Yeah, thank you.
Okay, I can take another 1 or 2 more quick questions before we proceed to the next speaker.
Thank you.
Yeah, thank you. So our next speaker is Professor Chen Yong from this Hong Kong University of Science and Technology, the Guangzhou campus. Okay, so let me quickly introduce about this Professor Chen Yong. So Professor Chen Yong is currently the assistant professor at this HKUST in the Guangzhou campus, and then he received the PhD from this Sun Kwang University under the supervision of this Professor Nangong Pak. He is like the founder of this of the perovskite solar cells, and then he also after that he worked in as the postdoc as the SESTEC under this Professor Xu Guangmin, and then he actually published the many the good papers, like the many natures and science papers. So without further delays, I would like to invite Professor Chen Yong to share this about your research.
Okay, thank you very much for the Professor Kell's introduction, and thank you for invitation. Invite me to this webinar. Can you see my PPT?
Yes. Yeah, can see very
Okay.
clearly. Yes.
Okay. I'm Yong Zhang from the Hong Kong University of Science and Technology, Guangzhou, and I'm in the Sustainable Energy and the Environmental Thrust. Today is my great honor to have this opportunity to give a talk at Photonics webinar. And the title of my talk is High Purity Precursor with Film Structuring for High Performing Perovskite Solar Cells. Next, I will following this outline, first introducing the background of perovskite solar cells and the research projects I did and the summary. So what is perovskite? Perovskite is initially a mineral that discovered in a Russian mountain and then named by the Lev Perovsky. Later, perovskite is a structure. Materials with the ABX3 structure could be the perovskite. The calcium titanium oxide is the typical perovskite structure. But for solar cells, A could be cesium material ammonium armadinium. B is lead or tin. X is halide like iodide or bromide or chloride. Perovskite have the compositional tuning properties that can make it have the different properties such as the different band gaps, and it have the higher absorption coefficients that make perovskite do not need fabricate very thick, and its longer diffusion length can facilitate the carrier transport from the perovskite to the electrode. And perovskite solar cell efficiency is developing very fast during the 15 years. Now the certified efficiency this year is almost approaching 27%. It's over the 80% SQ limit. So perovskite is showing the high potential for even the higher power conversion efficiency. But for perovskite film used in the solar cells, normally most of films are polycrystalline, but it have the drawbacks of disordered orientation and grain boundaries that will result in the defects inside the perovskite film. Although we say that perovskite have some certain level of defect tolerance, but if we want to fabricate higher efficiency, removing these kind of defects is very important. So what's the defects from? We can see that the preparation process of perovskite film, it needs the precursor preparing and spin coating or bar coating to fabricate the film, and then anneal to crystallization. In this process, the defects may originate from the precursor impurity and also the AB composite, the stoichiometric ratio difference could result in the bad reproducibility. And the perovskite film, the crystallinity and also the phase segregation is important for the lower the defects. Even the interface materials, especially the buried interface, could have the properties to make the good perovskite film. So my research is focused on these three parts, and first project is precursor synthesis. We try to synthesize the high quality perovskite precursors to make the low impurity inside, and also the good perovskite film, and also the interface engineering to make the higher efficiency. The first one is synthesis of high quality of perovskite powder. My talk will mainly focus on this part and tell about the thinking route of my research. For the perovskite precursor, traditional precursor is using the lead iodide and the ammonium iodide mixture. That if we need fabricate high efficiency, we require higher purity of the raw materials, lead iodide. This will increase the cost of the precursor price, and then the various stoichiometric will result in the poor reproducibility. Here we propose a method different from the traditional precursor, that we use the crystal precursor by first synthesize the FAPBI3 perovskite crystal first, and then redissolve this kind of crystal to fabricate the film. By using this method, we can synthesize these precursors starting from very low cost raw materials and lower the result precursor cost, and then control the accurate the stoichiometric in the result precursor to make the higher reproducibility and the high efficiency solar cells. And we can also synthesize environmental stable precursor to have the good storage stability and the phase stability. Actually, this idea comes out when I was a PhD in SKKU. And at that time, we found that perovskite grade lead iodide, 99.999% lead iodide is the price is even 21 times higher than the low grade 99% lead iodide. For the future, if perovskite commercialization, the perovskite panel 1 gigawatt will require 16 tons of FAPBI3. So this is have the huge market of the precursor. But if we purify the lead iodide from low grade 99% to 99.999%, is even need higher cost due to the higher thermal consumption. So we think we can directly purify the lead iodide from the lead iodide to the perovskite. During this synthesized process, we can purify this lead iodide by removing some impurities. So at that time, I proposed a room temperature synthesis method that using the acetonitrile as the solvent. In this method, we dissolve the methyl ammonium iodide first and adding some low-grade 99% lead iodide by stirring, and we can see that the black precipitate occurs. And if we filter and the washing, we can get the MAPBI3 perovskite powder. The synthesis mechanism is because of the MAPBI3 have the limit solubility in the acetonitrile. So in this reaction, we have the precipitation and the dissolution dynamic exist in this reaction. By extend the reaction time, we can improve the MAPBI3 precipitate quality. And by using this method, we can also use in the FAPBI3 perovskite crystal powders. We can synthesize the delta phase, alpha delta mixed phase, and also the alpha phase perovskite powders, and as well as the result different kinds of phase perovskite film. We compare this kind of powder microcrystal powder precursor with the conventional precursor mixture. in this work, we optimized the reaction condition to get a high yield of 93% delta phase of PBI3. And by dissolving this kind of precursors compared with the conventional precursors, we make the perovskite solar cell device. We can find that it shows the improved fill factor and the open circuit voltage, and have the higher reproducibility with the 1030 device have the average power conversion efficiency of 20.7%. And at that time, we get 21.07% quasi-steady state certified efficiency. But our previous work is that quantitatively characterization of the perovskite quality. But what's the real main impurity inside the precursor or the raw materials? After I graduate, I joined the SUSTEC and measured using the ICP-OES. We found that the main impurity inside the raw materials and the precursors is the calcium, sodium, and the potassium. We're using the DFT calculation, found that the calcium ion could result in the shallow defects and also the change the band gap of PBI3. So this kind of impurities, calcium ion mainly exist as the calcium iodide, which is low solubility in our previous solvent acetone nitrate, but have higher solubility in the water. If we can use water as the reaction solvent, which may be efficiently remove this kind of impurities in the precursor. So we try to use water as the reaction solvent. But as we know, perovskite is very unstable in the pure water because of this reaction. PBI3 could result in the FAI and the lead iodide because of the different solubilities in the water. The FAI could dissolve, but lead iodide could have the limit solubilities, make it precipitate. But we found that FAPBI3 could stable in the hydrogen iodide water solution with the clear solution, and also the precipitate color do not change. Then we try to find why could this happen. We compare the several kinds of solvent used in the perovskite solar cell, compare the Guttman-Donner number and the dielectric constant. The Guttman-Donner number is related to the Lewis space ability. If the Donner number is high, it could have the higher ability to coordinate with the lead iodide, then make lead iodide dissolve. And the dielectric constant, if the value is higher, they could have the ability to dissolve the ionic compound such as FAI. We found that our previously used acetone nitrate is in the center of this of the water position. So if we can change the water dielectric constant, then we can maybe the stable. This is the reason of the stabilizing the FAPBI3 and the synthesized, and it's possible. So we try to increase the hydrogen iodide concentration in the water solution. We can find that if the concentration is high, the solubility of FAI is decreased, and the FAI solubility increased. Then the solubility of the reaction compound is higher than the FAPBI3. This reaction or the perovskite FAPBI3 synthesis could be feasible to react. Then we use the very raw materials and the cheap materials, lead acetate and the 4-amino acetate with the 99% purity. In this reaction, they have the several steps of reaction. In this reaction, try to control the concentration of iodine ion is very important. If the ion concentration is lower, we will form the lead iodide as the impurity inside. But if the iodine ion is excess, then the lead iodide will dissolve to form directly the FAPBI3. So we try to control the pH value to control the iodine ion concentration, and we get a pH value lower than 1.9% is the optimized condition. Then we call this method is aqueous synthesized perovskite microcrystal method. Using this method, we can synthesize several kinds of perovskite microcrystal powders, such as delta phase FAPBI3, and the MAPBI3, and cesium PBI3 with good crystal shape and phase purity. And this method can also be extended to other kinds of 3D perovskites. Yeah, and this method can also scale up to kilogram scale with high yield of 92% and average purity of over 99.99% by removing the impurities inside the raw materials. And we calculate due to the raw materials cost is very low, we calculate the materials cost used in this reaction. We found that the price of the FAPBI3 microcrystal is like the $0.22 per gram. Then we use these three kinds of perovskite microcrystal to mixture to fabricate this composition of the perovskite film. We got 25.6% and the certified efficiency of 25.51% in the inverted PIN structure. My next project is perovskite film structuring there. As we know, cesium is commonly used to stabilizing the FAPBI3, and cesium and the FA is allowing should have the higher stability. But FA cesium mixed perovskite, we found that this kind of perovskite compositions will have the issues of FA cesium inhomogeneity. By the FA is enriched on the top and the cesium is enriched on the bottom. And this is because of the FA PBI3 and the cesium PBI3 crystallization rate is different, and make the perovskite film composition, the band structure is different. This will affect the charge transport. Here we try to introduce the PSP as an additive in this FA cesium mixed perovskite. We found that the PSP can control the crystallization rate of FA and the cesium perovskite, then make the homogeneity of perovskite film in the out of plane. Then we can efficiently charge transport. By using this method, we fabricate the device based on the PTAA whole transporting materials and achieving the over 26% with a certified efficiency of 25.8%. The third project is the interface engineering. Interface engineering is very important for the achieving high efficiency of perovskite solar cells. Especially the emergency of self-assemble monolayer SEM is very important for the inverted structure. They bolster the PIN structure to over 26%. But this kind of SEM has the like the ME4PAC, they have the poor surface wettability on the perovskite precursor solution. This will result in the numerous tiny holes and poor crystallization at the buried interface, leading to the interface recombination due to the numerous defects. So we introduced the buried interface molecular hybrid method by mixing Me4PAC with the natural tribenzoic acid, Na, to improve the wettability and also the distribution on the ITO substrate, and also passivate the perovskite buried interface. And by using this method, we got 26.5%, which is one of the highest efficiency at that time. And the device shows the higher stability. Then I can make a summary that we have did some jobs on the perovskite microcrystal precursor synthesis, and also perovskite film structuring and interferential engineering. And we got high quality perovskite microcrystal precursors synthesized from 99% raw materials to 99.99% perovskite precursors using aqueous synthesized method. And also we fabricate high quality perovskite film by cation homogenization, and also the interferential engineering to make the perovskite efficiency higher. So here I would like to thank my PhD supervisor Nanku Park and the Professor Baoming Shi and other cooperators. And thank you for your attention.
Okay, thanks, Daniel, for the very nice presentation and very interesting. Yeah. So I have the question for you like this. For this the inhomogeneity of this Fa and Cs, right? So in that case, I think that is the very similar to the halide segregation, but here your case is more like the cation, like the segregate. So this kind of situation, do you see at the normal condition, or like but for example, like the halide segregation, we only see this kind of thing is there in the end of the light illumination. For this the Fa and Cs in more homogeneity, you see like at the normal condition, like the room temperature, or like the end of the dark condition, or what kind of the condition is like make this case more serious?
Actually, we find this kind of condition is the normal spin coating process that we can observe this kind of condition, and no need other like some light or thermal. Maybe thermal is needed because this is we measure this kind of phenomenon after annealing. Yeah, we think this kind of inhomogeneity is because of the crystallization rate is different, because of the session is more easy to crystallization, and then the Fa is then later than crystallization. This make the cancer of the session will be enriched on the bottom, and the Fa is enriched on the top.
Yeah. So you think that is based on the energy during the crystallization process, yeah. And then
Yes, yes.
you determine this is the went from this using the energy, you measure the energy bandgap, and then you see the different energy gap. So
Yes.
other than that, do you have any other evidence for this kind of the inhomogeneity?
Oh, actually, I didn't show the data. Actually, we use the top themes to determine this kind of homogeneity, and also the high resolution TM, and also the in-depth XPS. We have the several kinds of the characterization to prove this. Yeah.
Understand. Yeah. Yeah. And another question is when you are in the is the donor number. When you talk about the donor number in this in the first project, yes. So what do you mean by the donor number?
Like the donor number is like the is related to the Lewis space properties. Yeah, Lewis space is we can give the electrode electron to the lead iodide with coordination with the share the electron with the lead iodide. So this related to the donor number. Yeah.
Okay. So in this project like this, instead of start using the very high purity precursors, you try to during the process you can purify at the same time, so you can make the perovskite. Is it this kind of idea? Because your final thing is like also like you need to purify it, right? You need to purify their all the impurity element. So, but instead of starting from the very purified precursor materials, you process somehow during the fabrication methods, and so that you can get the very purified perovskite.
Yes, it's possible actually. I have told
because
that.
I believe my understanding is that you still need to do the purifying it in order to get the high efficiency device.
Yeah. You mean we can directly purify it from that very raw like lead iodide, high purity lead iodide to make the higher efficiency. Yeah, I think it's possible. But thinking about the cost, if the 99.99% the lead iodide is expensive.
Yes. Right. Yeah, I understand that you compare the cost. Yeah. So in your case, it's like you don't need to purify for the precursor, but you need to purify at the same step, right? So but I didn't catch this point. So which step do you purify the remove all the impurity?
Which step? Oh, okay.
Yeah.
It's actually the synthesize is similar with this kind of reaction. Actually, during the dissolution and storing, the impurity will dissolve in the solvent because the calcium, sodium, and the potassium is easily dissolved in the water.
Right? Yeah.
In the water, yeah. And then we filter and get the precipitate, and then this impurity will dissolve and then
So meaning
removed.
that you still need to do the purification, right? But your purification process is a much more efficient and then cost effective than buying the purified precursor. Am I right?
Yes.
Yeah. Okay. All right.
Thank you.
Okay. Thank you. So I think we are there almost. This is actually this is running almost that I think we are running out of the time. So I think this maybe we can take like a very quick 1 or 2 questions. Do you see any question from the chat box?
No.
There is no question from my side, but if anyone has any question, please feel free to open your mic. I see that someone raised their hand, so I will allow them to talk. So please ask your question directly if you would like.
Hello.
I have one question from Dr. Yongjong. He introduced his amazing work, especially talking about commercial scale, which is targeted research. Do you have focused on the toxicity of lead? What was the main reason to choose lead instead of other elements?
Pardon? You mean the try to using other materials that replace lead? You mean?
Yeah.
Oh,
Why you have selected lead?
oh, actually, lead-based perovskite is the now highest efficiency compound. Now, I also try to do some synthesize process to synthesize lead and the tin mixed. This is the more lower band gap. Just try to using the tin to substitute the lead and actually this we also do some tin-based perovskite actually. Maybe other people concerned about the lead problem, right?
Yeah. Okay,
yeah,
thank you.
but this is the highest compensation. So we just synthesize now, and then maybe later we will do some lead and tin based perovskite microcrystal. Yeah.
Okay, got it. Thank you.
Thank you.
Okay, I think I think no more questions or comments for this. So in that case, I think I would like to thanks all the speakers for the sharing their interesting work on this the webinar on this advanced material for energy photonics. Yeah, so I think I will hand over back to this Arenas. I think, do you have any closing remarks, or do you want to make announcement anything before we end the session?
Yes, thank you, Dr. Kyo, and thank you to everyone who attended this webinar and who presented their work. I think it was a very valuable discussion. And once again, we have posted a message on the chat. So basically, the recording of the webinar will be made available as early as possible on the webinar website. And if you have any questions regarding the certificates of attendance, just access sciforum.net and you will find them under my certificates. So thank you once again for your time. And if no one has any question or closing remarks, I think we can end the meeting here.